Welcome students. Myself Dr.Monika Khetarpal. I am Associate Professor of Physics in Government Dongar College, Bikaner. I welcome you all in the enlightening session of MSc Final Physics. In this we were dealing with the fifth paper, that is solid state physics. Today we will discuss antiferromagnetism. We know that in a material there are large number of spins. We will consider the orientation of these spin. If we have a material in which all the spins are parallel, then that material will be ferromagnetic. But if we have a material in which the orientation of spin is in such a way that in the neighboring lattice site the spin are antiparallel, then such material will be antiferromagnetic. And the exchange integral factor J also defines the difference between ferromagnetic and antiferromagnetic material. If exchange integral is positive, material will be ferromagnetic. But if it is negative, then material will be antiferromagnetic in nature. So today we will discuss antiferromagnetic material. That is, we are going to discuss the material in which the orientation of spin of neighboring lattice site is antiparallel and the value of exchange integral is negative. In such type of material, the magnetic moment is 0 because number of spins which are aligned parallel equals the number of spin which are aligned antiparallel. Example of such type of material are MnF2, MnO2. Here I have plotted a graph between susceptibility and temperature. We can see clearly that if we increase temperature, susceptibility rises with temperature and it is maximum at a certain point which is termed as Néel temperature. After this Néel temperature, the susceptibility decreases. Néel temperature is denoted by Tn. Néel was a scientist after which it is named. So these materials behave antiferromagnetism nature below a temperature Tn and susceptibility follow a paramagnetic behavior above the Néel temperature. And from here we can see that when the temperature is 0, the magnetic moment of the sublattices are compensated and the net magnetic moment is 0. But as we increase the temperature, then there is a disturbance in the antiparallel arrangement, hence the material will have some magnetic moment. So susceptibility increases and this increase continue till a temperature Néel temperature. And at this maximum temperature Néel temperature, the orderly spin arrangement vanishes altogether and an antiferromagnetic material turn into a paramagnetic. So we will discuss the molecular field theory of antiferromagnetism. For this purpose, I am assuming that there are two sublattice array denoted by capital A and capital B, and we have assumed that the nearest neighbors of A atoms are B and similarly the neighbors of B are A. Now we will consider the different type of interaction which are arising in this antiferromagnetic material. In this antiferromagnetic material, there will be three types of interaction, and that will be the interaction of spins in A sublattice with the spins in B sublattice. There will be AB interaction, and there also will be AA and BB interaction. Let the molecular field of these two sublattices are HMA, this is of A sublattice, and the molecular field of B sublattice is HMB. Now I am applying an external field which is denoted by capital H. So we will write the effective field of A and B sublattice. Since the interaction is antiferromagnetic, we will denote the interaction by minus alpha and minus beta. Let AA and BB interaction are represented by minus alpha, and AB interaction is denoted by minus beta. So the strength at A field is H minus alpha Ma, because I have taken the interaction strength between AA by minus alpha, and the molecular field, the magnetization at A site is Ma, and the magnetization at B site is Mb. So H minus alpha Ma minus beta Mb, similarly HMB will be H minus beta Ma minus alpha Mb. Let my temperature to be greater than Néel temperature. So the magnetization of lattice A will be Ma will be n mu square upon 3 kBt Ha, because in a paramagnetic material susceptibility is inversely proportional to temperature. Here mu square is mu b square g square j plus 1. Here j is the total quantum number and g is Linde factor, n being the total number of atoms per unit volume. Similarly, we can write the magnetization of lattice B as n mu square upon 3 kBt Hb. Hence, the total magnetization will be M will be Ma plus Mb. So, collecting these two terms, n mu square upon 3 kBt Ha plus Hb. We have already written the formula for Ha and Hb. Substituting this, I can get the value of magnetization to be capital M equal to n mu square upon 3 kBt. Here I have substituted the value of Ha and Hb, and solving this by taking these two terms of M together, I get my susceptibility to be, which is M by H, 2 n mu square upon 3 kBt 1 plus n mu square upon 3 kBt alpha plus beta. This can be expressed by multiplying it with the temperature T, chi equal to 2 n mu square upon 3 kb divided by T plus n mu square upon 3 kb alpha plus beta. Here in the numerator, I have substituted 2 n mu square upon 3 kb to be C, and in the denominator, I have substituted n mu square multiplied by alpha plus beta upon 3 kb to be theta. My susceptibility comes out to be chi equal to C upon T plus theta. This is the susceptibility for antiferromagnetic material, and we have already obtained the susceptibility for a ferromagnetic material to be chi equal to C upon T minus theta. On comparing these two, it is clear that in an antiferromagnetic material there is a term T plus theta, whereas in a ferromagnetic material there is a term T minus theta, and C is a constant which is a Curie constant. In this expression, which is of ferromagnetic material, the Curie constant is n mu square upon 3 kb, and if we compare it with the Curie constant for antiferromagnetic material, it is clear that Curie constant for antiferromagnetism is twice. So, we have obtained the formula for susceptibility for an antiferromagnetic material, and on comparison we can see the susceptibility for three types of material is: for paramagnetic 1 by chi is T by C, and for ferro 1 by chi is T minus theta upon C. For antiferro 1 by chi is T plus theta upon C, and C is Curie constant, and the relation between Curie constant is that Curie constant for antiferromagnetic is twice that of ferromagnetic material. So, in our today's lecture, we have discussed the nature of antiferromagnetic material when temperature is greater than the Néel temperature. Thank you students for watching.